Okay. We know that the Turing machine is introduced by Alan Turing in the year 1936, and it's the mathematical model for any computation. It has models the computing capability of a computer. We know the definition of the Turing machine. Normally, Turing machine means M equal to Q sigma tape symbol delta Q naught B as well as F. Q is the set of finite states and sigma is the input symbols, and this is the tape symbols. What are the values available in the tape? And delta is the transition function. Q naught is the initial state, and B indicates the blank because the Turing machine allows the change in the symbols in the tape. We are considering this B also. F is the set of final states. This is the model of the Turing machine. Any Turing machine, it contains the finite control, read, write, cut, and tape is divided into many segments, and all the values, input symbols are stored in the tape. This is the two-directional infinite tape. You can move either forward direction or the backward direction. This is a general transition function model. Delta of Q comma X equal to P comma Y comma right or left. Q is the state, and state can be moved to another state P, and X is the input symbol. You can change the input symbol, or without change also you may move the head right or left. This is the general transition function of the Turing machine. In this class, we will see the variants of the Turing machine. The Turing machines are the language accepts it. Generally, it accepts the recursively enumerable language. And here we will see some of the variants of Turing machines. First one is the Turing machine with stay option, Turing machine with semi-infinite tape, offline Turing machines, multi-tape Turing machines, multi-dimensional Turing machines, and non-deterministic Turing machines. These are some of the variations of the Turing machines. The first one is the Turing machine is stay option. In general, we are dealing with the Turing machine. After changing the symbols or without change of the symbols, the Turing machine may either move to left or right. If the Turing machine is designed to stay in the particular position itself, then that Turing machine is called as the stay option. This is the general Turing machine. Only one difference is there. Left shift, generally left shift and right shift is there. In this Turing machine, in addition to left and right shift, one more option is there, that is the stay option. This is what called as the stay option Turing machine. So instead of moving right and left in the Turing machine, if the head stays in the particular position itself, means that is called as the Turing machine with stay option. Now see here Q1, Q2. Here the state changes from Q1, Q2, reads the input symbol A and changes it to B. Again, stay in the same position. It means stay in the same position. After executing this one, initially this is the step. After executing itself, A is transferred into B, A is converted into B, but Turing machine stays in the same position itself. That is the stay option Turing machine. Consider ABS. Read this one, write and stay option. This is the general way to describe this one. It means A is converted into this, A is converted into B, and the head is remains stay in the stay option also. This is one of the modified version. In general Turing machine, there are two possibilities, left move and right move. But in this stay option, without any move also, we can design the Turing machine. That is the first variant of the Turing machine. Left move means after processing this one, here I am writing left, so the head moves to the left position. Right means after processing A is converted into B and it moves to the right position. When you see the head, it moves to the right position. Stay means converting this one and stay on the same position itself, means that is the Turing machine with stay option. The second one is the Turing machine with semi-infinite tape. Generally, it contains the infinite tape. That is, it may move either in the forward direction or left direction. General Turing machine, the tape moves right or left, both forward and reverse direction is possible. But in the Turing machine with semi-infinite tape, only one direction, it will move only one direction. The first one is the end marker, and remaining it will move only the rightmost position, means that is called as the Turing machine means with, when the read write head is the tape boundary, no left move is possible. Only the right move is possible, means that is called as the Turing machine with semi-infinite tape. Consider this one. Here, any Turing machine simulate, any normal Turing machine can be simulated as the semi-infinitive Turing machine. That is, we can convert the Turing machine into a semi-infinitive. For example, consider this is the Turing machine and which one is the reference point. This one is the reference point. Here using this one is the reference point. Okay, this is the Turing machine reference point. From this one, it may move right or left. Now we are going to design a Turing machine with semi-infinitive. I'm going to convert it into a semi-infinitive. If I want to convert it into a semi-infinitive, I will make it in a with 2 tracks. I'll make it with the 2 tracks. Here, my aim is in the semi-infinitive, the tape can move only one direction. How will you change it like that one? It's possible. How it is possible means, take this one. Here, this is the reference point. From there, you can use the forward direction or left moves. But semi-infinite means only one direction movement is possible. So it can be constructed by using the 2 tracks. I use 2 tracks. Okay, instead 2 tracks. The first one is kept in the first track. So semi-infinite means leftmost one is the end marker. Then move D, E, and remaining things. Keep the remaining things here. Similarly, in the next step also, here you write the end marker, that is the reference point. Then it's read out in this direction. So reverse the string and store it here, C, B, A, and the remaining things. Either one can be read out in a time. Here only one read out. If you are moving the forward direction, use this one. You are moving in this direction, use this track. So the standard machine can be simulated as the semi-infinitive. Anything, a variance can be converted into a standard format. This is the way to convert the standard into a semi-infinitive. And the next one is the offline Turing machine. Offline Turing machine in the sense, here one tape is read only. One tape is the read only tape, and another tape is the read write tape. In the offline Turing machine, there are 2 things: read only tape and the read write tape. In the read write tape, read only tape, it's marked in between the end markers. End markers are used to indicate this is the string. The given string is given, and for each and every function, there exists some modification that is given in the read write head. That means here you cannot change the content in this read write head. Cannot change the content in the first one. So only it's called as offline. That is designed in offline. The contents cannot be changed during the online. During the online operation, after seeing the string or after seeing the symbols from the read-only tape, this contents can be changed. So this can be used to check whether for this one is replaced. If you want to replace certain things with other things, you can use this type of Turing machine. But one of the tape content won't be changed during that operation, and hence this is called as the offline Turing machine. And the next one is the multi-tape Turing machine. The multi-tape Turing machine, here instead of single tape, more number of tapes are there in the Turing machine. Okay, generally single tape is there and one read write head and one tape is there. But multi-tape Turing machine, many read write heads and many tapes are there. More than one tapes are there, and for more than one tapes to process the content in the tape, more than one read write head is also there. Means that is called as the multi-tape Turing machine. Here the number of tapes is n number of tapes. States are same, but n number of states are there, and left and right move is n number of times available. This is the only one change in the multi-tape Turing machine. For example, consider the Turing machine with 2 tapes. Here n equal to 2. Okay. In this example, 2 tapes are there. So Q0, initial state is Q0. 2 tapes are there. This is one tape. This is the another tape. 2 tapes are there. So 2 tape heads are there. After processing this one, if you are changing this A into X, and here head is move left. And here at the same time, the same input E. You read the same input E, and this E is converted into Y, and tape head moves right. So here I am performing 2 operations simultaneously. For parallel processing purposes, we are using this kind of Turing machines. Here parallelly 2 processes are carried out in a single state. State is Q0. State changes from Q0 to Q1. Okay. state changes from Q0 to Q1. And the input symbols are A and the E are the input symbols. This A as well as the E are the input symbol. After processing this A is converted into X. So after processing this A is converted to X. Instead of only one input symbol, here two tapes are there. So I am using two input symbols. So this A is transferred into X and E is converted into Y. Then either head can move left or right. Here there are two tapes, hence we'll write two left or right operation. First tape moves left. When you see this figure, this moves left. So first one is the left operation and this one moves to the position of right. So this is the right operation. So in the multi-dimensional and the multi-tape Turing machine, more number of tapes are there and more number of heads are also there. Based on our requirement, this is smooth. Suppose three inputs are there. Here only two tapes are there. Again, I am including one more tape, tape 3. And the tape 3, I am going to convert this G. I am going to convert this G into, next time I am going to convert into H. G into H. And if I move right, the position move right means we should include that also. Initially, Q0, A and E is there. Now I have included one more tape and the tape content is F. Here you write F. One more tape content is added. Then I have changed this F into H. So A is converted into X, E is converted into Y, and F is converted into H. So include H here. And for this one, this is move left, right. And for example, here I move this right means to include that also. Based on the number of tapes, the transitions, number of tuples in the transitions can also be changed. That's the concept of the multi-tape Turing machine. And the next one is the multi-dimensional Turing machine. In the multi-dimensional Turing machine, yeah, the Turing machine can generally the Turing machine can move the right direction or the left direction. Okay. In the multi-tape Turing machine, n number of heads are there and n number of tapes are there. But in the multi-dimensional Turing machine, only one tape is there. That is divided into multi-tracks and multi-dimensions. And here, the only one difference is the head may move left, right, up, or down. Four directions are there for the multi-dimensional. The head movement may be either up, down, right, or left based on the given position. Consider this is the two-dimensional Turing machine. Here two-dimensional. The head can move right, left, or up and down, and these are the two tracks. This one is 1, 1, and this is 1, 2, like that. If you want to move this position, you give this position to the Turing machine based on that head is moved in the particular track. So by using this concept, you can place the position head anywhere else. After processing this one, you may directly place the head here. That is down, left, left. By using this one, you may process it here. Or use left, left, right. If you are giving the position, this is suppose this position is 2, 1 means if you give the position, automatically the head tracks the second row, first column. Okay, second row and first column, that is placed, the head is placed here. So in this multi-dimensional Turing machine, only one head is there, but the head can be moved in upper position, lower position, right hand position, or the left hand position. That is the concept behind the multi-dimensional Turing machine. And the next one is the non-deterministic Turing machine. We know that deterministic means for a single symbol for processing Q, A. Q, A means it will goes to only one direction, only one state, either Q1 or Q2 one state. It may change or not change. Suppose I am changing A into X and right or left. This is the general deterministic Turing machine. There's a deterministic path. After processing this A, it will goes to the location Q1, changing this A into X and move right. Non-deterministic means for the input symbol, if more than one path is there, multiple paths are there, that is what called as the non-deterministic Turing machine. Example for non-deterministic, consider there is state Q into tape symbol is there. Then for the non-deterministic, it may follow any two power n number of things are there. So when you are writing this one non-deterministic Turing machine, Q into tape symbols may lead to, it may maps to 2 power Q into 2 power n elements should be mapped here. That is the non-deterministic Turing machine. Okay, so deterministic means always the transfer function q into lambda map to q into this same tape symbol only. But non-deterministic means it may go any transition. If n states are there, 2 power n transitions are possible for this non-deterministic Turing machine. For example, consider q1 comma a. Either it may follows this one. A is converted into B and it moves left, or A is converted into C or it moves right. Two possibilities are there. It may select the first choice or the second choice. Hence, this is called as the non-deterministic Turing machine. For example, consider A. For processing A, this is the tape. After processing A, B, C. After processing A, it may convert it into B and goes left. This A can be converted into B and it will go to the state Q2. Goes to the state Q2, move left, and A can be processed into B. Or another choice is for the same A itself, this figure can be converted like this one. A may be converted into C and this moves right. This is also possible. The Turing machine don't know whether it selects this path or that path. Hence, this is called as the non-deterministic Turing machine. This is more powerful, but it can process in 2 different dimensions. But the thing is, if it is not correct, the processing is not correct, we require the backtracking. So this is called as there is no deterministic path. Hence, this is called as non-deterministic Turing machine. And next one is the multi-head Turing machine. Here, a single tape is there, but multi-heads are there. Each head will move independently. That is the multi-head Turing machine. In ideal, this kind of Turing machines are not available. And next one is the multi-track Turing machine. Multi-track Turing machine means a same thing, but tape is divided into many tracks based on the problem. It's divided into many tracks, but the head is same. It's divided into many tracks means that is called as the multi-track Turing machine. Here, in the multi-dimensional, head may move up, right, down, or left. But here, there is no movement like that. Each and every track is modified separately. For calculating some purposes, for some subroutines and all, we use this kind of Turing machine. So multi-track Turing machine is a specific type of multi-tape Turing machine only. Multiple tracks, but one tape head is there. Only one head is there. In the multi-tape Turing machine, so many heads. If number of tape is n, then n heads are there. Same time itself, you can modify n tapes. But in the multi-track Turing machine, many tracks are there. Only one head is there. For example, you want to calculate the multiplication of 3 numbers. Multi-track Turing machine can be used to find the multiplication of 3 numbers. Here the multiplicand is, here m is multiplicand is given there, and number of times, how many number of times you want to multiply, that is given in the second track. Then we know that the multiplication is the repeated addition. The repeated addition is performed and this is modified in the track or 3. For example, you want to multiply 5 into 3. Here m is equal to 5 and n equal to 3. 5 is the constant one. You are going to add 5 each and every time, and that is placed in the first track. In the second track, first write 3. Okay, first write 3 and initially the answer is 0 only. First it's filled with 5 and in the second track, first write 3 and the answer is 0. Hence, then you add 3 times, repeated addition. First you add these two contents, 5 plus 5 or 1 into 5. Okay, 5. You are going to add this one. First write this 5. This 5 is placed here. This is the general simple technique used for multiplication. One time you have added. Okay, so initially the value is 0. This 5 is added with the 0. These two values are added and that is placed here. One time it's added. If it is added one time, in the track 2, you are not content in the track 1. You are going to change the content in the track 2. Now track 2, 3 is decreased to 2. Okay, now it's decreased. Again, you add these two contents. Because here also you added the first track contents as well as the third track content. These two contents are added and the second track content is decreased by 1. The same thing is repeated again and again. Again add these two tracks. These two tracks are redundant. 5 plus 5 equal to 10. Place it in the tracks 3. 10 is placed here. Now what is the next step? Decrease the value of track 2. This is decrease. Then 2 is decreased to 1. Now it is 1. Again add track 1 and track 3. Add these two values. 10 plus 5, 15. Move one position right and place that value here. Okay. Then now decrease the value of this one. Now it is 0. If it is 0, that's completed. No need to add it again. So this manner, it will be performed. The multiplication will be performed. So generally, this multi-track Turing machines are used to perform certain specific applications. So that all about the differences of Turing machines. So you see here the different varieties of Turing machines are. First one is Turing machine with stay option. Turing machine with stay option means in addition ordinary Turing machine, the states, input symbols. In addition to that, in the move, generally we use left and right move, but Turing machine stay option, you are included one more option, stay. Without any change also, you may implement, that is the stay option Turing machine. And second one is the Turing machine with semi-infinite tape. Instead of using the infinite tape, semi-infinite tape is also possible. In this case, left end marker is the fixed one and the tape can be extended in the right hand direction. If it is the ordinary Turing machine, that can also be converted into a semi-tape Turing machine by this concept. By using two tracks, you will write this one. The forward directions are given and the reverse direction strings are reversed and write it in the second tab. So the standard Turing machine can be converted into a semi-infinite tape Turing machine. The next is the offline Turing machine. In the offline Turing machine, one tape is the fixed one. You cannot change the content in that tape. And the second tape contents can be changed. Multi-tape Turing machine. Here, n number of tapes are there and n number of tape heads are there. Number of tapes increased and number of tape symbols also increased. And based on that, left and right move is also possible. A multi-dimensional Turing machine means here it is similar to the multi-tape Turing machine, but only one head is there. It can be moved in 4 directions. That is the multi-dimensional Turing machine. And next one is the non-deterministic Turing machine for a single state and for the single symbol. If there exists more than one move is there in the Turing machine, that is called as the non-deterministic Turing machine. For a single state and single symbol, 2 power n number of moves are possible in the non-deterministic Turing machine. And again, the next one is the multi-head Turing machine. Here, each and single tape itself contains multi-head. Each and every head is acting in an independent manner. And last one is the multi-track Turing machine. It's mainly used for some specific application. Here, the tape is divided into many tracks. Only one head is there and the tape is divided into many tracks. Based on the application, the head moves and change the value. Example is the multiplication can be performed by using the multi-track Turing machine. These all are about the variants of Turing machines. Next class, we will see the different types of languages that can be accepted by the Turing machine.